Okay, friends, in this lecture, we are going to study about wind power, wind power, uh, also the principle and working of wind turbines. First, we'll see how wind power emerged in power systems. In olden days, people used windmills to generate electricity in rural areas. So initially, it was used only to power rural areas as electricity was not there in rural areas. Um, then, when transmission lines began to transport electricity to rural areas, that is when grid infrastructure was in place. In 1930s, the windmills slowly disappeared. Then in early 1970s, because of oil shortages, people were more aware of the uh, green energy sources and its importance. So they were eager to use alternative energy sources. Then the re-entry of electric windmill was seen in USA. But today's wind machine is very different from yesterday's machines or the machines which we used in olden days. Those machines were used primarily to convert kinetic energy into mechanical power. Kinetic energy into mechanical power. Because and this mechanical power was not used to generate electricity, rather it was used to grind grain or pump water. But today's wind machines are primarily used to generate electricity. Okay, so um, today's wind machines use blades to collect the wind's kinetic energy. So the blade will look like the blade looks like uh, an aerofoil, and when the wind hits the blades, it rotates. The kinetic energy from the wind is extracted by the blades, and the blade rotates, and the blades are connected to a generator through a shaft. So the generator will generate electricity, which is connected to grid. Okay, this is the grid. Okay, now so the wind flows over the airfoil shaped blades, causing a lift. Lift means actually this vector could be decomposed into uh, horizontal and vertical vectors. So if the aerofoil is like this, and if this is the vector, then like this and like this. So this is the lift which lifts the blade and which causes the rotation, and this is the drag. The horizontal component is a drag. So the drag force will slow down the wind turbine, and the lift force will move the wind turbine. We'll see in detail these things. The aerodynamic side of wind turbine we'll see. So basically the wind flows over the airfoil shaped blades, causing lift, like the effect of aeroplane wings, causing them to turn. Then the blades are connected to a device shaft that turns the electric generator to produce electricity. The modern wind machines are having problems with um, the production of electricity when the wind is not steady. of course, naturally itself, the wind is not steady. The wind flow is not steady. Its velocity is always fluctuating. So accordingly, the power produced by the wind turbine is also fluctuating. So there should be some control in place to make the output power from the wind turbine steady. Now, large turbines are connected to utility power networks and some other type of generator. Uh, no, when large turbines are connected to utility power networks, then at times of low wind speeds, the wind power output will be less. So some other type of generator should pick up the load when there is no wind. But small turbines are connected to diesel or electric generators, or sometimes it has a battery to store the extra energy they collect when the wind is blowing hard. That means when the wind speed is very high and if the load demand is low, then that energy could be stored in a battery. But if the wind turbine capacity itself is high, if it is large, then the battery size should be large, so it may not be economic. So for small wind turbines this works, the storage works. For big wind turbines it may not work. Now coming to the aerofoil design, let's see how the aerofoil design is there. So 1 minute, let me take that note. Okay, so the energy in the wind, how is the energy in wind used? So here let this be a circle, that is the wind blades are encircled by this area, right? So this is some area. Then so the wind velocity is v, it's blowing through this disk area, right, which happens to be the wind turbine rotor. It's actually blade, but the swept area. Okay, so this is considered as the swept area A. This is considered as the swept area A, and this is the wind velocity V. Okay, now since the moving air is not a solid mass but a fluid, this mass m can be written as rho A into d. Rho A into d, where d is the distance, A is the swept area, and rho is the density. So here it's density of air, okay, which is normally 1.225 kilogram per meter cube. Let me write it here, 1.225 kilogram per meter cube. Okay, now V is the wind speed. V is the wind speed in meter per second. Okay, now we know that power equals work by time, but here work is kinetic energy by time. Now kinetic energy E contained in the wind is what is tapped by the turbine. So the kinetic energy contained in wind, which is P kinetic, equals half mv squared, where v is the wind speed in meter per second. Now m equals rho ad, so which we have already seen here, right? M equals rho ad. So this m equals rho ad goes here. So half into rho ad into v squared, right? Rho ad into v squared. So density rho, area A, and distance d. Okay, distance d. Now the air density also affects the power produced, because the air density varies as a function of pressure and temperature. So since the pressure and temperature vary according to the installation site, because the altitude of the installation site with respect to sea level is, if it is different, then the pressure and temperature will vary. So the combination of pressure and temperature affects the air density. Now, so the air density could be derived as rho equals rho naught minus 1.194 into 10 raised to minus 4 into h, where h is the height above sea level. H is the height above sea level. H is the height above sea level. So the place in which we install wind turbine, the height of that place above sea level, and rho naught is the standard density. Standard density 1.225. So this is the standard density, but the actual air density will vary according to the installation site, the height of the installation site. So how it varies, that depends on this equation. Now, when a volume of air passes through an area A per unit time, then d becomes 1, the distance becomes 1. So m will not be rho ad, instead m will be rho a. When a volume of air passes through an area A per unit time, distance becomes 1. So the mass of the fluid, here it's air, it is equal to rho into A. However, when mass flow rate of air through this area is with velocity v, if it is with velocity v, then you have to multiply this with v, velocity v. Okay, so basically the m equals rho, distance became 1 and rho a became rho a into v, because now we consider the air with velocity v or wind with velocity v. So accordingly the mass also, the mass flow rate will change because it hits at a higher force, a larger force when the velocity is more. So the mass flow rate is more. So here this m equals rho av goes here. Okay, half into rho av into v squared. This is half mv squared. This is m. This is m in half mv squared. This is the kinetic energy. So this will become half rho a v cube. Half rho a v cube, or half into mass flow rate into v squared. Mass flow rate into v squared. The total power contained in the wind flowing through the swept area A, which we have considered here, the swept area A, which we have considered here, is equal to half rho a v cube. Now, this half rho a v cube is now in watts. So this is P total. P total. This considers everything. This considers the installation site. This considers the wind speed. It considers the density of air and the variation of density of air with respect to the location, everything. So the total power that is extracted from the wind when it hits when the swept area is A and the velocity is v, is half rho a v cube. Half rho a v cube. Yeah. Now let's move on to the next topic. Before moving on to the next topic, the power in the wind is proportional to, let's have some insight from this equation. The power is now proportional to wind speed cube, right? V cube. So it is it's crucial to site the wind power plant, because the wind speed of that particular site is very important, because it's actually the power that can be produced from the wind power plant installed there is proportional to the wind speed cube, right? Now let's see an example, a small example. Calculate the total wind power in an area where the average wind speed is 6 meters per second, 6 meters per second, using a wind power plant with a 60 meters rotor diameter. Okay, rotor diameter. So here 6 meters per second is the average wind speed. Wind speed equals 6 meters per second. 60 meters is the rotor diameter. Now air temperature is 25 degrees Celsius with a density of 1.225 kilogram per meter cube. Now we know that if you want to find the total wind power, P total equals half rho A V cube equals half rho into pi r squared, because it's a circle, right? Pi r squared into V cube. Now it's equal to half into 1.225 kilogram per meter cube is the density, into pi into 60 meters is the rotor diameter, so 30 meters is the rotor radius, so 30 squared into what is V cube here, average wind speed is 6 meters per second, so 6 cube. Okay, 6 cube. Now this is in watts, the answer is in watts. So if you want to find it in kilowatts, you can divide it by 1000, then you will get approximately 374 kilowatts. So this is the total power that can be extracted from such a wind site where wind speed is given and the air density is given and the swept area is given. Okay, so that is what. Now if in this example, if the wind speed is 4 meters per second, then what will happen? So earlier the wind speed was 6 meters per second. Instead, if it is 4 meters per second, then what happens to P total? P total equals half rho A V cube, half into 1.225 into pi into 30 squared into 4 cube, right? Now if this 4 is increased to 8, if the wind speed is increased to 8, what happens? The same equation we will use, but here the answer will become, so P total for let's say P total for V equals 4, we get 110 kilowatts. Then P total for V equals 8 is 886 kilowatts. So it is seen here that when the wind speed doubles, when the wind speed changes from 4 meters per second to 8 meters per second, the power increases by 8-fold. It's almost 8 times, right? Approximately 8 times, maybe some 8.05 times 110 to 886 kilowatts. So that is a insight we get from the relation between total power extracted and wind velocity. Now let's see the aerofoil. and the aerodynamics of wind turbine. So here, let's say the aerofoil is like this. The aerofoil is like this. Now, the wind is coming like this, suppose. Then, as we have discussed, it can have two different components like this. This is the drag, this is the lift. The lift is what rotates the blade or the turbine. Now, the angle at which the wind hits the blade is known as the angle of attack. Angle of attack. So this angle is very important when we, for calculation of lift, or when the angle of attack varies, accordingly the lift also varies. So the power output from the turbine also varies. Say if we have a low angle of attack alpha equals 2 degree, say, so we have some lift. Now when alpha equals 9 degrees, the lift increases. Then when alpha increases, the lift also increases till the critical angle. Till the critical angle. So let the critical angle be 16 degree. So after 16 degree, beyond 16 degree, if the angle of attack increases, the lift decreases and the drag increases. That means the power output will decrease. Power output will decrease because the lift is the force which moves the turbine. Drag is the force which tries to slow down the turbine. Okay, so this can be used, this principle can be used to control the power output of the turbine, because at very high wind speeds, if the turbine itself is is prone to damage, if the turbine itself is prone to damage, or if the turbine blades are prone to breaking, then this control is known as stall control, stall action, where after the angle of attack, the stall action gradually sets in, but the lift force is the drag force is greater than the lift force, and the blade rotation stops. When the drag is more, the blade decelerates and it will stop. So this is a braking action, or the control of power output could be done using this principle. So that's all with the fundamentals of wind turbines. Now we'll just see what are the generator types used in wind turbines. There are basically three types of generators used in wind turbines. First one is squirrel cage induction generator. Then they are normally used in fixed speed wind turbines. Fixed speed wind turbines. Then the second one is doubly fed induction generator, and the third one is permanent magnet synchronous generator. Three types of generators. So with this, I'm stopping here. I'll share some lecture notes with the block diagram of wind power plant. You can go through that also. Thank you.